Welcome back. This is video lecture 29.2, and we're going to talk about section 2 in chapter 29, the force between two parallel currents, or maybe more specifically, two parallel wires, very long, straight wires, parallel to each other, each carrying electric current. We will discover, if we were to actually set that up in the lab, that they exert a magnetic force on each other. We want to be able to calculate that. Okay? It enables us to practice using the results from section 1 of this chapter and an important result from chapter 28 as well. Okay, so two long parallel wires, each carrying electric current. We're going to calculate the magnetic force that one wire exerts on the other. So here's the situation in a sketch. There's a wire A and a wire B, and they're actually very long and straight. So they actually go on and on and on, this way, this way. You're just seeing a segment of each. And they each are carrying conventional current this way. And the current is I sub A in wire A, and I sub B in wire B. And the straight line distance between them is D. Okay, that's the situation. That's all it is. Okay. All right. Our task is going to be to take a certain length of one of the wires, like right through there, and calculate the magnetic force on that length. How is that going to happen? Well, it's because of the following. Wire B is, of course, immersed in a magnetic field created by the current in wire A. We now know that current creates magnetic field. Wire A carries current. So wire A creates magnetic field everywhere. Wire B is immersed in the magnetic field of wire A. Okay? And from last chapter, we know that a current-carrying wire in an external magnetic field can experience a magnetic force. And that's where the force on wire B is going to come from. So the first thing I have to figure out is, at the location of wire B, what is the magnetic field created by wire A? And we're going to denote that B sub A, magnetic field created by the current in wire A at the location of wire B. Okay, like right there. Okay, all right, now we just found in section 1, we just learned how to find the magnetic field created by an infinitely long straight wire. That's what wire A is, so we can use that result. And that result tells us that if you have an infinitely long straight wire carrying current, and you know the current in it, and you know your distance from that wire, the magnitude of the magnetic field created by the current in the wire at the location where you are is given by this formula right here. This is just the magnitude for right now. BA magnitude is mu0, that new constant, permeability constant, times I sub A. I want the current in wire A, over 2 pi d. D is the distance that we are from wire A. I'm imagining that point I've marked with the little x there. That's a distance d from wire A. And that's the magnitude of B sub A. What's the direction? Now, I mean specifically at the location there where the little green x is. What is the direction of B sub A? Direction of B sub A there. That's where we are, as it were. We learned a kind of a specialized right-hand rule for figuring out the direction of the magnetic field created by the current in a long straight wire. Remember how you think about that For a long straight wire, the magnetic field lines circulate around the wire, and you use this specialized right-hand rule to figure out which way they circulate. Put your thumb in the direction of the current and see which way your fingertips curl. So if I put my thumb in the direction of the current IA, my fingertips curl as I look from this one side clockwise. So if I try to draw a magnetic field line, okay, I probably didn't draw that very well. It's perpendicular to that line, okay? They circulate in a plane perpendicular to the wire, and they circulate clockwise. So the point is, at the location where the X is, the magnetic field B sub A points, if you like, straight down. Okay? Straight down. Trying to draw a circulation. Okay? That is perpendicular to wire A and passing through the place where the X is, and the magnetic field points straight down. That's the direction of B sub A. Let me show you here. Okay? That's the direction of B sub A due to the current I sub A at this location right here on wire B. Now, the good news is it's that same magnitude and direction anywhere along wire B. Here, or here, or here, okay? Same magnitude and direction everywhere along wire B. And straight down, so another way to think about that is it's perpendicular to wire B. All right, now we're going to focus specifically on this length between these two little tick marks. That length, and we're going to calculate the magnetic force on that length of wire B. Okay? Calculate the magnetic force on length L of wire B. Force. I'm going to denote it FBA. That means the force on wire B due to the current in wire A. That's what that notation means. And here, I just refer back to the result from chapter 28. That if I have a straight segment of wire in a uniform magnetic field, to calculate the magnetic force on that segment, I use that formula right there. I take the current in the wire, now we're talking about wire B, so notice it's I sub B, times L cross B, big B, the magnetic field. Now the magnetic field is coming from the other wire. That's why it's labeled capital B sub A. And then the L vector is drawn here in this next picture. It's got a length equal to the length between those two tick marks, and its direction is the same as the current in wire B. Okay, so that's how they get the L arrow there. And the B, capital B sub A arrow is already there. All right, let's work out first the magnitude of that force. I'll put in the details over here to the side. Let's find the magnitude of the force on B due to A. It comes right from this cross product right here. That's I sub B times magnitude of L, magnitude of capital B sub A, sine of the angle between L and capital B sub A. Look right here. What's the angle between L and capital B sub A? Did you say 90 degrees? They're perpendicular. And what's the sine of 90 degrees? +1. So what's our expression for magnitude FBA? Well, I'll write it like this. That's the way all the books would write it, where everything means a magnitude. But we just wrote down the formula for the magnitude of B sub A. It's mu 0 I sub A over 2 pi d. You got to keep track of the roles that are being played here. And what we're in the calculation we're doing here, wire A is the source of magnetic field. And wire B is sitting in that magnetic field. Okay? All right, so when I write all this out, for the magnitude of FBA, I'll have I sub B times L times mu 0 I sub A over 2 pi d. And if I want to just kind of consolidate that a little bit, you can write it like this over here. For the magnitude of FBA, you have mu 0 times L times I sub A times I sub B over 2 pi d. Handy little formula. It's not very difficult to use. But now here's an interesting question. What's the direction of FBA? Right? What is the direction of the force on wire B due to wire A? Do you see how to get that? Think about that for a minute. Let's talk about it. Well, did you say that I'll get the direction for FBA from the direction of L cross BA? It's that cross product that's going to give me the direction of the F. So I need the right-hand rule. But the picture down here shows the L and the BA. So we ought to be able to use the right-hand rule and get the direction. Why don't you try that? Pause the video if you need to, get an answer for the direction of FBA, and then come back. Okay, did you use the right-hand rule? You can feel free to use the 2-pen method, as I recommend. I'll use a red pen for L and a green pen for BA. And as I look at the picture, I hold the red pen in the direction of L and the green pen in the direction of BA. I hold them with my left hand with a common tail. Then I reach in with my right hand and push the L on top of the BA. And it's got to be perpendicular, this cross product, to both L and BA. And that force turns out to be directly towards wire A. Okay? That way. Directly towards. That's the direction of the force on B due to A. There it is. See it? Well, that means if the force on wire B is directly towards wire A, that would be an attractive force. Okay? Wire B experiences an attractive force towards wire A. So the force is attractive whenever the currents in the wires are in the same direction. See here? IA and IB, same direction. And the force on B due to A, towards A. That's an attraction. Okay? All right, now, I want to ask some more questions about this. That's all well and good for the force on B due to A. Let's figure out the force on A due to B. What about force on A due to B? Arrow. I want a magnitude and I want a direction. Might want to take an intuitive guess first, right? What do you guess about the magnitude and the direction of the force on A due to B? And why is there a force on A due to B? You see why? Well, what we just did for the force on B due to A was based on the following line of reasoning. The current in A creates magnetic field everywhere. Current B is immersed in that magnetic field and therefore can experience a magnetic force. Now just reverse the roles. Current B creates magnetic field everywhere. Current A is immersed in that magnetic field, and therefore current A can experience the magnetic force. I want to know the magnitude and direction of that. Okay? All right, did you make an intuitive guess? Now let's be formal and show what we get. Here would be how you would start that calculation. Force on A due to B. I take the current in A, then I do L cross magnetic field of B, big B sub little b. Okay? Let's try to draw those things into the picture over here. For wire A, I'll take that length. Well, L vector in the direction of the current. Now, that's the L vector right here. What's the direction of big B sub little b? So now I'm talking about this point right there. What's the direction at that location of big B sub little b? Try that. Okay, now you've got to put your thumb in the direction of I sub B and look which way your fingertips circulate around wire B, and then look where you are relative to wire B. You're over there where the green X is. And when I use this special right-hand rule for the current in wire B, I get a magnetic field at the location where we are that's straight up, perpendicular to wire A. That's big B sub little b. That's a right angle right there. Okay? So you need to be able to figure that out from the specialized right-hand rule. Now the magnitude of it, what would that be? Big B sub little b. Well, the current in wire B is just long and straight. The current is I sub B, so it would be mu 0 I sub B over 2 pi, and the distance is d. That's the magnitude. And so you do the right-hand rule for the cross product there, and you'll get the magnitude of FAB. You can go through the steps. You'll get mu 0 IA IB L over 2 pi d, just like we did for the magnitude of FBA. Okay? They have the same magnitude, FAB and FBA. But what's the direction of FAB? Try that. All right, did you do the right-hand rule where you crossed this L on top of this B sub B? And then you should discover that the force is to the right, i.e. that way. There it is, okay? FAB. Attractive, right? Wire A is attracted to B, just like wire B is attracted to A. And those two forces have equal magnitudes, but opposite directions. Okay? All right, now here's another question that's important to consider. Let's clear out some of our writing here and our drawing. And here's the question. What happens to the force, or the forces, if the currents in the wires are in opposite directions? All right? Okay, so the way we'll do it, there's a couple of ways you could do it, is I'll come over here to the side. And I'll draw the parallel wires again that are a distance d apart. And let's take the current in A to again be that way. But now let's reverse the current in B. So it's going that way. And let's take a little region here. My bad. Beg your pardon. Is that right? Of wire B, let's label it L. Like so. Do you see why I chose the L that way? Because it's got to be tangent to the wire and in the direction of the current. Now I already know, since I didn't even touch the current in wire A, that its magnetic field there at the location where we are, B sub A, is downward. If this is a right angle, it's still a distance d between the two wires. So the magnitude of the force is the same as it was before, when the currents were in the same direction. But what's the direction of FBA? You need to use the right-hand rule, yes? And do L cross BA? What direction do you get? Do that carefully. You get that the force is now on B, due to A, is away from A. Okay? That means wire B is repelled from wire A. And the same would be true for A. It's repelled from B. So what we say is, parallel currents attract each other, and anti-parallel currents repel each other. And we just went through all the steps to see how you come to that conclusion. Now let me show you just another picture, but this is with a Wiley Plus animation. So here we see, we've even got set up a whole set of axes, X and Y and Z. We've got two long parallel wires in the YZ plane with the wires parallel to Z. And positive currents are going upward in the plus Z direction. And IA and IB are both positive. IB is 1.5 amps, I sub A is 1 ampere. It shows us IB going upwards. See there, the red? I sub A is also going upwards. And then what it shows along various lengths of wire B is the magnetic force on it. Force on B due to A. And it's attractive because the currents are in the same direction. Notice the currents don't have to be equal, they just have to be in the same direction. So these green arrows represent the force on B due to A along various length segments. What are the green arrows? Do you see them there? What do you think those are? That's the magnetic field due to A at the location of B. And from that specialized right-hand rule, that's in the negative X direction. And then we do the right-hand rule of L cross B, where the L would be going up, and that's how we get the force on wire B to the left. Now if I click the button up here, it'll show me the force on A. So how will the picture be different? Can you predict? Let's see. All right, notice the B here is now the big B due to little b. Notice its direction. There's the current, I sub A. And then there's the direction of the force on that segment of A due to B. Attractive. All right, let's go back to wire little b. Now I'm going to take one of these currents, maybe I sub B, and reverse its direction. So it'll become negative 1.5 amps. Notice what happened. I didn't touch wire A. So now wire A's current's going up, and wire B's current's going down. We call those anti-parallel. And now notice the force on B due to A is away from the other wire, away from A, repulsive. That's also true for wire A. The force on wire A is away from wire B, again, repulsive. I can even change D, the distance. If I make the distance smaller between the wires, what's going to happen to the force? It's just going to get bigger in magnitude. See how those blue arrows are getting longer? The green ones too. The wires are closer together. Farther away. They get weaker. The force gets weaker. Okay? All right, so that's an interesting physical situation, and it gives us a good opportunity to practice with some of these physics ideas. So the only other thing I have is a class engagement. For the force between parallel currents. And it goes like this. We have three long, straight wires that are parallel to each other and equally spaced. And you can see them there. You're looking at them from the end on. Okay? And they have identical currents that are either into or out of the figure. The dots represent current coming out of the screen towards you, and the X represents current going into the screen away from you. let's just say that current is I. The same. I. But look at the directions of them. Let's say the distance between neighboring wires is D. All right, here's our task. Rank the wires according to the magnitude of the force on each due to the currents in the other two wires. Greatest first. So what you in essence have to do is you have to find a symbolic expression for the net force on wire A, the net force on wire B, and the net force on wire C, given their locations there and the directions of their currents, and then rank them from largest to smallest. Don't do that too quickly. Use the results of what we've just been talking about for two parallel wires and just take them in pairs. Okay? But you got to find an expression, there won't be numbers of course, for the net force on wire A, the net force on wire B, and the net force on wire C, magnetic force. All right, and then we'll be talking about this kind of physical situation in class as well. That's all for this video.